Good evening, everyone, and welcome. My name is David Ellis. I have the privilege of serving as the interim executive director of the Harvard Museum of Natural History, a sponsor of tonight's lecture, and it's the first of our fall series being given by Professor Charles Langmuir, which I will say more about in a moment. But I do want to mention that throughout this fall, we are presenting a series of 9 events. They appear on a card which you can pick up to the right, my right, as you leave. And what we bring to you, we hope, is the best of Harvard, or at least some of the best of Harvard, of the work of Harvard faculty and students as they try to understand ever better the Earth, past, present, and future. The other thing I want to convey in the way of a pitch is to encourage you to think about membership in the Harvard Museum of Natural History. It provides free admission, incidentally, not just to the Harvard Museum of Natural History, but also to the Peabody Museum, in case you haven't enjoyed that opportunity as well. It's also special events and activities that many people find interesting and enjoyable. Lastly, there's a list there where you can sign up for regular emails, and we hope you will. And next Wednesday, there will be a talk here about invasive species and New England forests. You may have seen a recent comment in the paper about a beetle that has now decided to invade. But that talk will be by David Orwig and David Foster from the Harvard Forest. And there's more, so please pick up one. Now, I mentioned just a moment ago that our mission is to highlight the work that faculty, Harvard work, do in the area of Earth, planetary science, life sciences, to better understand our planet. And frankly, there's no one better to talk about this than our speaker tonight, Professor Charles Langmuir, the Hooper Professor of Geochemistry in Harvard's Department of Earth and Planetary Science. Charlie has built a distinguished career through his investigations of numerous aspects of the solid Earth's geochemical cycle. Responsible for discovering hydrothermal sites in 3 ocean basins. He's led more than 20 research cruises over the last 2+ decades, including the first investigation of the Arctic Ocean ridge system, which you may have seen described in the front of papers. He's a fellow of the American Academy of Arts and Sciences, has received numerous distinctions, including the prestigious N.L. Bowen Award and the Holmes Medal from the European Union of Geosciences. Now, it's not totally surprising because Charlie earned his baccalaureate here at Harvard and his PhD from the State University of New York at Stony Brook. His dissertation research focused on major and trace elements in basalts. He's been at Harvard since 2002 after spending 20 years with Columbia University's Lamont Doherty Earth Observatory. And tonight he's going to be talking about the new edition of his and Wally Brecker's landmark textbook, How to Build a Habitable Planet, the Story of Earth from the Big Bang to Humankind. Conveniently, there are copies for sale tonight. Some of you, I noticed, were already buying some. And I understand Charlie's willing to stand around and autograph some. So we're going to have a wonderful lecture, some fabulous ideas to think about, and to think about not just tonight, but to think about in the time ahead, as our sustainable world, we hope, is something that we can all contribute to. That's my pitch for tonight. Charlie, please.
Thank you, David. Well, tonight I want to talk to you about this beautiful object. And I'll talk about it in sort of the perspective of a book that I've been working on for the past decade called How to Build a Habitable Planet. And this book is a expanded and revised edition of an original that was written by my colleague, Wally Broecker, who is one of the great scientists of our country and also the founder of the term global warming, and has had an incredible career of great discoveries spanning about 50 years of research. Wally wrote the original of this book, which is this right here. And he came to me one day and said, you know, I wrote this book, How to Build a Habitable Planet, but I have a lot of other things I want to work on. Maybe you would like to rewrite it. Because the strange thing was that it's how to build a habitable planet, but there was no biology in it. So I said, sure. I know no biology, but I said, yeah, I'd be happy to try to contribute to writing this book. And 10 years later, there it is. Wally had the incredible vision of trying to tell a scientific story in more colloquial language than is normal for a textbook, and that was able to encompass a grand scale of scientific investigation, going from the Big Bang, which was the first chapter of his original volume, up to a chapter at the end, which he called Mankind at the Helm. And that vision of looking from the beginning to the present-day crisis is what I've tried to do in the rewrite of that book. And Wally has revised a couple of his original chapters and edited many of mine, including telling me to throw one out. But he felt our writing styles were sufficiently different that it would seem weird to have individual chapters written by each of us. So in this new and expanded division, we've added life, we've added plate tectonics, we've added the whole concept of planetary evolution, and we've incorporated the scientific advances of the past 25 years. 25 years ago, mid-ocean ridges were just beginning to be mapped. Hydrothermal vents had not been discovered. Dark energy and dark matter were not in anybody's mind. There'd been no discovery of planets around other stars. Climate science was still in its initial stages. So the past 25 years have seen incredible advances that we've tried to take into account. The book is a textbook, but it is also something that we have tried to pitch at the boundary between textbook and that accessible to the interested layman who could skip over some of the more technical parts. And you'll probably get a feeling for that in this lecture tonight also, as I try to talk about some of the main points that I hope people who read the book take home with them. There'll be some places where you can sort of fuzz over your eyes and wait for the next slide to help the overall story move along. And what I'd like you to take home tonight, if possible, is three perspectives. The first one is the incredible scale of time and space that the story of our universe encompasses. It encompasses about 40 orders of magnitude in both time and space, inconceivably large numbers to us. Nonetheless, even as our puny representatives of this puny planet around a puny star in one of 100 billion galaxies, it is awe-inspiring to me that we as human beings can begin to encompass this overall story. It instills a sense of wonder, which is one of the things that I hope that we are able to convey. The second thing is this idea of planetary evolution with two aspects to it. One is planetary evolution is increasing relationship among the various parts of the planetary system and among biological organisms and within biological organisms. And the third one is planetary evolution as a series of energy revolutions. And the most recent energy revolution has happened in about the last 100 years as we have gained access to fossil fuels and other forms of artificial energy. Finally, from these perspectives, I hope that our view of ourselves and of human civilization is somehow informed, particularly as we face the great challenge of human civilization, which is how we can relate effectively to our planet making use of its resources without destroying it. So we begin at the beginning, which is the Big Bang. And one of the things that we try to do in the book is establish, get rid of words like, do you believe in the Big Bang? Or at my daughter's wedding a year and a half ago, I was there sitting down next to a guy. It happened to be down in Virginia. And he sat down next to me. He said, so, you're an earth scientist, huh? And I said, yes, I am. You know, everyone likes earth scientists. And he says, so, are you a believer in Al Gore's theory? And what we want the students to be able to say is not, I'm a believer in this, or I'm a believer in that, or are you a believer in the age of the earth, or a believer in plate tectonics, or a believer in evolution. But do you understand the actual facts upon which these arguments are based? And so can you make your own assessment of what is true and what is not on the basis of the real evidence? So there's a lot of really great evidence for the Big Bang, which I'm not going to go through, but is gone through in one of the chapters of the book. And it happened about 13.7 billion years ago. It's the initiation of everything existing, everything we know, everything we can know, every object within the universe. And within that Big Bang, there is everything that exists was created. 96% of it is stuff we know nothing about. That is dark energy and dark matter, which make up the overwhelming majority of the universe. Of the remaining 4%, most of it is hydrogen and helium, and so we're left with about 0.1% of universal creation, which makes planets and life that can then reflect on this overall majesty that confronts us. Now, the Big Bang only makes the elements hydrogen and helium, so that's not much good for making planets and things like us, based primarily on carbon. And over the next several billion years, there's the formation of the elements, until about 4.55 billion years ago, our solar system forms. So time is moving to the right on this diagram. And our solar system forms here at 4.55 billion. We go through 4.5 billion years of Earth history until recently, about 150,000 years ago, Homo sapiens appeared on the scene, and of course human civilization a few thousand years ago, and technology about 100 years ago. The universe is amazingly vast. This is a picture of one small quadrant, not even a quadrant, one small morsel of the night sky, and in it you can see all of these objects which don't look exactly like stars because they're not, they're galaxies. So the universe contains a few hundred billion galaxies. One of those, a few hundred billion, 7 billion people on Earth, so if there were 100 Earths around, all of them populated like us, then our galaxy would be one member of the universal constellation of galaxies, and we would be one citizen among this 100 planets. So our galaxy is a little item within this grand universe. It's only 100,000 light years across. 100,000 light years across, we want to talk about communicating with other civilizations. We send out a radio signal over here and we say, hi, how you doing? 100,000 years later, it reaches our neighbor over on the other side. He says, I'm great, how are you? And 100,000 years later, the signal gets back. It's a hard way to have a conversation. And our sun is in what's called the habitable zone of the Milky Way galaxy. Of course, we're not able to sit outside the Milky Way galaxy and look at it, so this is a cartoon. And the inside probably has too much radiation to be hospitable to life. And on the outside, probably not enough heavy elements have been created to be able to make things like planets and life. Now, within this galaxy, the heavy elements that we need are made from large stars, and so there are about 400 billion stars in our galaxy. 400 billion stars in the galaxy, 400 billion galaxies in the universe. We're one of those stars. We're a little tiny star. And the large stars are essential because they have short lifetimes of 1 million years or so, and then they explode in spectacular supernova eruptions, one of which was probably the star in the east that is referred to in the Bible, that these are occurring periodically throughout the Milky Way and are of great excitement whenever they do happen for the astronomer community. And these elements are extremely important because they have short lifetimes and they make the heavy elements. So they're fertilizing the galaxy with the necessary elements for planets like ours and life. And small stars like our sun come along, and because they're small, they don't burn so bright and they can last a long period of time. So they may have a lifetime of about 10 billion years. We're 4.5 billion years through that lifetime, so the Earth is middle-aged, still going strong. And that long lifetime is necessary in order for planetary evolution to take place that has enabled a planet to develop intelligent life like our own. So our little sun is this guy, a small star, one of 400 billion stars within our galaxy. And around it formed a series of planets, one of which is the Earth. And here's the Earth's size relative to the sun. Scale. Now, one of the remarkable features of us as human beings is that despite our incredible minuscule size and inevitably minuscule importance within the universe, nonetheless, as many of us just felt when we saw this, there is a sense of relationship. There is a sense of wonder within our small brains where we are able to have a relationship with the cosmos. We're able to perceive these things and have them influence how we feel and how we think. And this ability to have that kind of relationship is only a capacity of intelligent life, I think. I go to Martha's Vineyard in the summer, and there was a beautiful sunset, and I was taking a walk looking at the beautiful sunset. I walked down, and there was a post. And on the post, there was a crow. And the crow was just sitting there, peaceful, looking at the sunset. I wondered. Maybe he thought it was as beautiful as I did. But nonetheless, despite the magnificence of crows, except when they wake you up when they caw in the morning, there is this sense of relationship that we can experience that is something unique to us as human beings. And I want to talk about relationship as one of the aspects of planetary evolution, because one of the wonderful things in being able to think about the Earth on the kind of scale that you need to think about it when you're telling the whole story is that I realized that in one way of looking at planetary history is to view it as an increasing set of relationships involving the solid Earth, the atmosphere, and life, and also within living organisms. So the moon tells us something about the conditions of the early Earth. And when we see those conditions on the moon, it is an essentially lifeless object. It's been banged a lot by meteorite impacts. That's why it has the cratered surface. It has no atmosphere. It has no ocean. It has no movement. It's a lifeless and kind of planetary fossil. And the Earth would have looked something like that early in its history. Plate tectonics would not have developed. The temperatures of a stable climate would not be there. No life existed. All the planetary cycles that maintain Earth today would not yet have begun. And today, we see Earth as a fully integrated system. I intentionally put this slide up because ordinarily when people think, oh, let's see a picture of Earth, then you see pictures of this part. And this is just all covered with blue. And we have, national boundaries and state boundaries and blue states and red states and good countries and bad countries. And we have all these associations associated with the black part. But the really dynamic part of the Earth, where most of the action is taking place and the exchanges are occurring between the Earth's interior and exterior, occurs in the ocean basins, which are sort of like a membrane over Earth's interior and are revealing to us what's going on underneath. And one of the aspects of the oceans, and one thing that's been discovered primarily in the last 25 years in detail, is this global system of ocean ridges. It goes up the Gulf of California, cuts across on the San Andreas Fault, and comes out on some ridges up here, circles around the Pacific Ocean. One limb of it goes over here underneath Chile, Another circles around between Australia and Antarctica. It goes up and is splitting Africa along the Red Sea, goes around Africa and runs up the center of the Atlantic Ocean on the Mid-Atlantic Ridge, through Iceland and up into the Arctic Ocean. 62,000 kilometers, 80% of Earth's volcanoes, most of Earth's energy output happens there, most of Earth's volcanic eruptions happen there, and most people don't even realize it exists. When I go up to people and I meet them at a cocktail party and I say, "Did you realize that if ocean ridges did not exist, you could not exist?" They look at me as you might expect. As a friend of mine once said, "You've got to find a better opening line." But I've spent my life studying these things, and in particular, we had the excitement of being able to go into the Arctic Ocean. This is Greenland here, Spitsbergen, and this is one of the endpoints of the ocean ridge system, which extends across the Arctic and ends up over here in Siberia. And because it was covered with ice most of the time, it was not able to be investigated. So we went up there with mighty Healy, the U.S. Coast Guard cutter here, and this was the maiden voyage of the Healy, and so for safety we also sailed up there with the Polar Stern, which was a well-seasoned German icebreaker. The mighty Healy, 25,000 pounds of ice-breaking steel. It's a Coast Guard ship, so it's painted sort of battleship brown on battleship gray on the inside. The food's not that great. It's got a bunch of Coast Guard cadets. If you want to take off on the helicopter platform, you have to give a day's notice, and then Coast Guard people get out there with fire-protected suits on, and you fly off, and you can land over on the Polar Stern, where you find a sauna, 3 bars, a pool. And if you want to ride in the helicopter, you just say, "Hey, can you take me somewhere?" And the guy's dressed casually, goes out, hops in the helicopter, says, "Sure, hop in," and off you go. So we sent our people over to the Healy for reward. They sent their people over. We sent over to the Polar Stern for reward. They sent their people over for punishment. And then one day the call came in, "We're stuck in the ice. Can you come and get us out?" Now, the Coast Guard was feeling pretty bad about everybody saying how great the Polar Stern was. And so the Coast Guard, with sort of standing up a bit straighter, steamed across the ice and broke the Healy free. And the commander said, I was up in this conning tower up here taking video of it, and he said, "Can you send me that?" So it was great excitement. We got to go to the North Pole. The landscape up there looks something like this. And one of the things you realize when you go on one of these vessels and study ocean ridges is you're not alone. You are out there. I like to study the rocks, but you have geophysicists wanting to study the bathymetry. You have people studying the gravity. You have biologists wanting to study the life associated with the ridges. You have people wanting to looking at what's happening in the water column. It's inherently interdisciplinary, and everyone is trying to work together to understand the ocean ridges as an interconnected system that includes all these fields, every one of which throws light on what is happening in the other. And so we investigate these ocean ridge volcanoes. These are not volcanoes from the Arctic, but instead of the vision of Mount Fuji or something that you might have on land, it's this long linear crack that is opening as one plate spreads to the east and another spreads to the west. The crack opens, the magma oozes out of the middle as a wound that never heals, circumnavigating the globe. And when you go down close to those, you find sometimes hydrothermal vents. These are at temperatures of 400 degrees centigrade. They have these amazing life forms, unlike anything found on land, that are surviving in the bottom of them. That was one of them mating, by the way. And these tube worms are animals that have no stomachs. They make use of a bacteria farm in their gut to provide food for themselves. So this is the place where there are these interactions between Earth's interior, fueled where the volcanic heat from the volcanoes is fueling a thermal environment which gives rise to these hydrothermal vents, which supports living communities at the bottom of the ocean, which sends these fluids up into the ocean, which are essential for seawater chemistry, and circulates fluids through the ocean crust, modifying that ocean crust, which takes these chemicals back down into the Earth's interior, and turns out to be central for how continents are made. Everything related: biology, volcanoes, seawater, making continents. all as parts of a single system. Now this is driven by plate tectonics, and here's how the continents have moved over the last 250 million years. And just to guide your eye, here is South America, there's Africa, we have Antarctica, India's about to take off over here, and down here's Australia. Starting at about 100 million years ago, India goes on a voyage northwards across the Indian Ocean. It slams into Southeast Asia, forming the Himalayas and squirting out Southeast Asia like from a toothpaste tube. Earth is in movement. And this movement is something that maintains Earth's surface in a habitable zone. And it's one of the important aspects of the Earth is that it's the relationship between the interior and the exterior, where all the parts of the Earth system are related to one another, that has been able to preserve Earth as a habitable zone for 4 billion years. This linkage is done through something called the solid Earth plate tectonic cycle. So here we're looking at a cross-section of the Earth going down towards the Earth's interior at the bottom of the slide. And so here's your ocean ridge system where you'd have one plate moving this way and another plate moving that way. As this plate ages, it picks up water from the hydrothermal circulation. It travels tens of millions of years across the bottom of the ocean. Sediments rain down on it. Life dies and forms these sediments, goes back down into Earth's interior, releasing water and CO2, causing melting in the overlying mantle, producing volcanoes like Mount Fuji or Mount St. Helens, and sending volatiles up into the atmosphere. It seems maybe a bit arcane. It's the movement of the solid Earth, and yet it is Earth's long-term climate thermostat. So it is closely related to the CO2 cycle, and carbon dioxide is taken up by organisms and that ultimately create calcium carbonate on the sea floor. And so this calcium carbonate, which is limestone, needs both calcium and CO2 in it. And the animals make shells that sink down and go to it. Sometimes the calcium carbonate precipitates directly if there's enough calcium and CO2 around. That material then gets taken back down into the Earth's interior where it's released by melting, comes out the volcanoes, and goes back into the Earth's atmosphere. So how does this maintain climate? As we all know, CO2 is a very important feature of the greenhouse effect. And if we did no greenhouse effect, all of Earth would be below freezing. It would not be habitable. So some CO2 in the atmosphere is essential. Over long time frames, hundreds of thousands to millions of years, if CO2 gets too high in the atmosphere, it makes the rainwater more acidic, and that leads to more weathering of the continents. And that creates more calcium in the oceans because the calcium is produced by weathering. That combines with the CO2 and drops the CO2 content of the atmosphere down, cooling the planet. If the planet gets too cold, then the weathering stops. The calcium is not into the ocean. The calcium carbonate is not deposited, but the volcanoes keep sending CO2 up into the atmosphere, so the CO2 builds up in the atmosphere, and that enables the planet to warm, and it comes back to its habitable zone. So the relationship between Earth's interior, the oceans, weathering, the atmosphere, life, is all this coupled system creating Earth's habitability. And remarkably, we've had liquid water and a habitable surface for at least 3.8 billion years. Now, some of you may see on the internet or the news somewhere, you know, CO2 coming out of Earth's volcanoes all the time. So the amount of CO2 that the human people are putting in the atmosphere, it's no big deal because it's dwarfed by CO2 emissions that are naturally coming out volcanoes. We are a blip on the radar screen. CO2 coming out of volcanoes today, 0.1 gigatons. Human emissions of CO2 last year, 35 gigatons. So human forcing is 350 times the forcing that you get from volcanism, which is the primary mechanism for climate stability over Earth's history. This is what I mean by facts. If you hear a fact like that, you're struck. You don't believe in global warming or not believe in global warming. You just realize that human beings as an impactor on the planetary system are huge We're 350 times background on the primary cycle that is governing Earth's climate. Now, coupled with this change, this increasing relationship in Earth's functioning and the relationship among the parts, is increasing relationship of life. So the simplest life, probably from about 3.5 to 2 billion years ago, are bacteria, prokaryotic cells. They're very simple. Okay, that's wrong. They're not very simple. They're extremely evolved and wonderful organisms, but their structure looks very simple when you draw it on a screen. They have no nucleus. They have genetic material in a single fiber. A lot of their operations take place within their cell wall. They're 0.2 to 1 micron in size. A micron is 1,000th of a millimeter. They have a small amount of DNA. They can divide each 20 minutes, and they often thrive in the absence of oxygen, which means they're anaerobic. That's how we can get sick. You divide every 20 minutes. So divide every 20 minutes, 3 hours, you have about 10 lifetimes, one cell becomes 1,000. 3 more hours, the 1,000 becomes 1,000,000. 3 more hours, the 1,000,000 becomes 1,000,000,000. You're sick. So these guys have incredible capacity, incredible genetic diversity within them. In fact, most of the genetic diversity of life in the planet resides in these organisms, and yet they're extremely simple. And these kinds of organisms were present in the early Earth, and so what did the early Earth look like? It didn't have lots of trees and fish and all that stuff. It was bacterial slime. We say, oh, I'd love time travel. I want to go back to what the Earth was like a few billion years ago. You go back, you die. Okay. There's no oxygen in the atmosphere, there's nothing to eat, you just look around and there's slime everywhere. It'd be like, so we wouldn't recommend it. Now, as Earth evolved, and this is going to be closely coupled to a change in the composition of the atmosphere associated with oxygen, these small prokaryotes began to form partnerships. And as they formed partnerships and related to one another, there was the gradual evolution of the eukaryotic cell. Eukaryotic cells beginning roughly 1.5 to 1.7 billion years ago. They have 1,000 times more DNA. They divide in 24 hours, and they normally are aerobic, that is normally oxygen requiring. You can see that by being 10 microns more in one dimension, they're 1,000 times bigger in size. They're highly complex machines. They have these organelles in them, many of which are relics of the partnerships with the prokaryotic cells that formed partnerships to lead to this kind of development of relationship. Fellow eukaryotes. We are eukaryotic organisms, and as life evolved from the single-celled eukaryotic life to multicellular life, then the eukaryotes themselves began to relate and form partnerships. And so you can get animals like ourselves, in which we have about 250 different kinds of eukaryotic cells, all relating to one another within our bodies to create a single, relatively unified organism. And the structure of these cells actually shows this development of partnership, because actually a lot of these organelles are in infolding parts of the cells, showing that these things form relationships. They become enclosed, they lose some of their functionality, but still maintain some of their original DNA. Then once oxygen builds up high enough in Earth's atmosphere, you get the arising of multicellular organisms, like this is one of the earliest ones called a trilobite, beautiful examples of which you can see in our museum here. And then that has no vertebra. And then a few 100 million years later, you start to develop more complex ecosystems. This is a Devonian landscape a couple 100 million years ago. And there you start to see life that looks more similar to what we have today. But of course, life keeps evolving since that time. Here, for example, there were no mammals. But the evolution of mammals occurring after the death of the dinosaurs about 55 million years ago, where the mammals came to dominate the environment. So, Earth itself developed these relationships, and life developed these relationships, and life and Earth are intimately connected. And this is a kind of interesting kind of science because it's interesting, increasing relationships, development of feedbacks, partnerships, linking all the parts of the Earth. Nothing is isolated. So what kind of science is this? It's not the science you hear about in very exciting physics lectures, where the physicist might be able to tell you about going down to the smallest degrees of matter, string theory, where everything can be explained by the fundamental particles that make up all of matter. No, that's a reductionist and deterministic, often, perspective. It's a calculation of equilibrium. But we're now realizing that in the natural world, that a systems perspective is more relevant, which says that the whole is greater than the sum of the parts. That is, each of us as individuals is far more than just what we would be if you isolated all our cells and laid them down on a line on a table. And that understanding things requires the knowledge not only of the constituent parts, but of the relationships among the parts. And this gives a sense of meaning that cannot be discovered by isolating the parts. And this is the real world. This is the way the real world works. This is the way the Earth works. It's how organisms work. It's how stars work. It's how solar systems work. Increasing relationship. And relationship is what leads to the significance of objects. The second thing about planetary evolution is as energy transformation. And I just want to quickly walk you through the initial state of the Earth, which had very little ability to absorb and process energy, to the Earth today, which is a kind of planetary fuel cell that gives us immediate access to energy that would have been impossible earlier in Earth's history. Would you like to see some magic? Instant energy. It's amazing. If you go to any other planet on the solar system, if you go to the moon, if you go back in Earth history, you can't do that. We have this energy potential all around us that we live off of as we breathe. It's the same sort of reaction is taking place here, but in a controlled way. And Earth has gradually developed the oxygen, which is one half of the reaction, and the reduced molecules that are the other part of the reaction, the combination of which is energy release. And that combination of energy released is the release of stored energy from the sun that is gradually accumulated in the Earth's as a fuel cell over all of Earth history. So this history is the transformation of the planet, able to absorb and process more and more energy from the sun. And this transformation took place through what I like to describe as a series of energy revolutions, where life gradually transformed the planet from a lifeless surface that reflected sunlight to a living surface that transformed solar energy into life. So Earth is made up of these things. These are pictures of meteorites from our wonderful collection that we have in the museum. And the bright, I'm about to try to use this as a laser pointer. That's when I was walking to my office earlier this week, and I found myself clicking my car opener to try to get into my office door. Okay, these bright spots are iron, nickel, metal. And of course, metal's not stable on Earth's surface today, but there would have been metal on Earth's surface early in Earth history. And this is a beautiful Palasite meteorite showing the coexistence of olivine grains, which is the mineral peridot. You can see some of those in the mineral hall, and with the metal background hosting all of those. Metal is reduced iron. We all know what it looks like. We all know that it's gray. We all know what happens to it if we leave it out in the air. And when you look at Earth today, you find that the surface is red when it's exposed to the atmosphere. That is, all the iron metal, which is iron in the neutral state, and all the iron 2+, has been converted to iron 3+, which comes from the reaction with oxygen, to produce these magnificent soils, or magnificent rocks. This is one of the biggest iron mines in Australia, where this iron is mined for our civilization. And this sort of rusting of the Earth, this conversion of the Earth from an anoxic, oxygen-free surface to one which is oxygen-saturated, is part of the overall process of planetary evolution. So we call this a fuel cell because a fuel cell is a conversion of chemical potential energy into an electrical current. So in the cars, we would use hydrogen coming in, that's the reduced molecule, combining it with oxygen, and the conversion of those two together produces a movement of electrons, which is an electric current, which could light a light bulb or drive a car, and that reaction is controlled because the interactions between the hydrogen and the oxygen have to go through this loop rather than the two of them interacting explosively. So modern Earth is such a fuel cell. We have reduced carbon produced by life, and we have reduced iron and sulfur from Earth's interior interacting with the oxygenated surface produced by life to create aerobic life like ourselves, which makes use of this energy potential. That's why we can't evolve until that energy potential exists. And it also leads to much enhanced processes of things like weathering of the surface. So we have Earth. It has now the positive pole on the outside with the free oxygen. It has the negative pole on the inside with the reduced species in Earth's interior. And it also has a pole of organic carbon, such as in black shales and coal and oil, which is another very important part of the reduced pole, or it's in living matter as well, like plants, which we eat. And it's the interaction between this reduced carbon and the oxygen that provides the energy that we make use of. So Earth history can be viewed as the progressive charging of this planetary fuel cell. So this gets a little bit technical, but photosynthesis, for example, takes CO2 from the atmosphere, it combines with water. You have an energy source, usually from the sun, which produces this molecule, which is an abbreviation for an organic molecule. That's actually the glucose molecule plus oxygen. And during this process, the oxygen goes from its reduced state of 2- over here to a neutral state over here. It gives its electrons to the carbon, reducing the carbon, creating an electric potential between reduced carbon in this molecule and an oxidized reservoir in this molecule, making use of the sun, which makes that reaction able to occur. So this has occurred in a series of energy revolutions. Earliest life, there was no oxygen around, and it may have survived by eating organic chemicals that were made abiotically in the early Earth, because the early Earth was a reducing environment, like meteorites and the moon. And the first energy revolution was when microbes found the means to use light energy from the sun to make their own food. These are called autotrophs. And so they would take reduced molecule like hydrogen, combine it with carbon dioxide and solar energy to produce glucose plus water. You don't see any oxygen in these reactions. So this is not an oxygen-producing environment. Now there's a problem with this, because when you look at the species over here that are providing the hydrogen, you see it's H2, that's a very rare molecule, and H2S, that's a very rare molecule. You might also be able to use methane, very rare molecule. So you're limited by the reagents. And the second energy revolution was photosynthesis, where now the source of electrons and hydrogen could come from the water molecule, and water was everywhere. So life suddenly is no longer limited. It can expand and through photosynthesis begin to take over the planet. Of course, it's limited by other nutrients like nitrogen and so on that are essential for life. And it also has a big problem because it's producing this guy, free oxygen. I don't know how many of you take fish oil or eat blueberries. Why, you know that broccoli is the only healthy food. It's because they have antioxidants in them. Because oxygen is toxic. It's the progressive oxygenation of our bodies that may be a major contributor to aging. Because oxygen wants to react with this molecule and burn it up. And therefore it reacts with organic molecules and destroys them. So the early prokaryotic organisms were largely anaerobic. They weren't adjusted to oxygen. They didn't have antioxidants. They had no protection. So the creation of this oxygen, which is a boon because of the ability to undergo photosynthesis, is also a dangerous pollutant to the environment. So that will be limiting to the evolution of life at this time. Life is no longer limited by the rarity of these kinds of molecules. You have much greater access to solar energy, but you have a problem because the oxygen is toxic. But there's another remarkable thing about oxygen, which is that if you can use it to process glucose in a controlled way, it produces far more energy. So anaerobic respiration, that is respiration in the absence of oxygen, breaks down the sugar molecule to produce these products plus some energy. And when you do that, you get 2 ATPs. ATP is the energy currency of the body. But if you take that same molecule and you burn it with O2, then you go down all the way to CO2 plus H2O, reversing the photosynthetic reaction, and you generate 36 ATPs. 36 over 2, factor of 18. So imagine the organism that is able to make use of this reaction. Competitively, they're going to take over the world because they have access to 18 times as much energy as the organisms that are living in the absence of oxygen. So there's an evolutionary expression of the organisms that have to find out ways to protect themselves from the toxic effects of oxygen while still being able to use the oxygen that is present to generate huge amounts of energy. That's an energy revolution. When they're able to do that, it allows them to take over the world. The fourth energy revolution is multicellularity. There you can have active transport of oxygen to organs like we have. You have cell specialization. You have active transport of both the oxidized and reduced reservoirs. So we eat food, we breathe, we actively combine these things, thereby processing energy much more efficiently, rather than just relying on diffusion across cell membranes. And this leads to much increased networks and much greater energy usage. And multicellular organisms are then able to take over the world. The prokaryotes are everywhere. You have 10 million of them per square centimeter in your armpits. If they had a vote, there are enough prokaryotes in either one of us to win any election. So we're permeated by these more primitive cells, and yet we have become multicellular organisms because of our ability to process energy in this wonderful way. And this energy revolution is what allows a change of the world from being governed by these kinds of organisms to being ruled by these kinds of organisms, to being ruled by multicellular groups of these kinds of organisms like ourselves. So all this involves the progressive oxygenation of the atmosphere. And here we have time going across on the horizontal axis and a log scale of oxygen on the vertical axis. You have very little oxygen in the ancient past. You have a remarkable change in oxygen at about 2.5 billion years ago, but still only to about 1% of present atmospheric levels. And we're not really sure whether oxygen builds up gradually through this period or stays at some kind of steady state before it ultimately rises to the 21% oxygen we have in the atmosphere today. And this high level of oxygen is then what allows the emergence of life as we know it. But you'll notice this band is a very small portion of Earth history. So if we put Earth history on a circle, we have the early Earth when it forms. We have the origin of life here and domination by prokaryotic cells over more than 1 billion years. Then we have the formation of eukaryotic cells, again going over about 1 billion years. And then 600 million years ago, 542, about 15% of Earth history, we get the first primitive multicellular organisms, and then those evolve over the last few 100 million years until we have human beings appearing. Human beings are not this orange line. Human beings are the vertical edge of all of those lines. So the first fossils only happen here. All the fossils are only from the most recent 15% of Earth history. So life is planetary. Life can only evolve through the progressive change of the planetary systems and coupling with them. We are planetary beings. And life evolves in relationship with the planet and progressively modifies it to create this planetary fuel cell that is able to form a single integrated system that has remarkable stability and remarkable properties. And generally, we think this has happened through long periods of homeostasis, like the billion of years when prokaryotes dominated the Earth. It's supported by stable feedback loops. It becomes perturbed, for example, by the rise of oxygen, and then we see if that perturbation can lead to a new planetary state at the next level of complexity. And my colleague Andy Knoll and his colleague Bombach have divided Earth history into a whole series of steps, 6 or 7 steps, where you go from these periods of homeostasis and you get a remarkable change in the functioning of the Earth system, and it leads to a new form of planetary functioning. And in this process, the planetary evolution has proceeded by increasing access to energy and increasing relationship. Okay, now we're ready for humans. So what can we say about human civilization from these perspectives of planetary evolution involving these changes in relationship and energy? Well, we have the human energy revolution, the 5th great evolution of energy in planetary history. So this is watts per person use. And this line down here is at 100 watts. That's the amount of energy that we get from food. That's the amount of energy that all the other animals, the lions, the tigers, elephants, probably a bit more because they're larger. But we get 100 watts of energy from our food. We run on a 100-watt light bulb. Amazingly efficient. It's why when we get into bed at night and we cuddle up next to our partner on a cold night, they are a 100-watt heater. It's one of the great things. 100 watts. Now, we're very limited as long as we are restricted by that level of energy. And so in the United States today, each of us uses 10,000 watts, remarkably. We use about 100 times the amount of energy that we would get from food. 10,000 watts. Well, if you take your electric bill and you look at it in your home, you can see how many kilowatts of energy you're using during the month. Then you have all the energy you use from your cars. You have all the energy that's being used in this room. You have all the energy of the entire civilization. The global average of energy is 2,300 watts. You can see places like India and Latin America over here. Here's China and Canada and the United States, up at about 100, global average 2,300. It makes us supermen. We can leap tall buildings. We can fly as fast as a speeding bullet. We can see through walls. We can, with tractors and things, completely modify the landscape. It's the latest energy revolution in Earth history. And it's as great an energy revolution as the revolution that took us from anaerobic to aerobic metabolism, that allowed the complete transformation of life from being one run by very simple unicellular organisms ultimately to multicellular organisms. Remember, that was a factor of 18, a factor of 23. That's what allows us to completely dominate the Earth's surface. That's what makes us unique in overall Earth history. And we've been able to do that because of our access to Earth's treasure chest. Earth built up treasure over 4.5 billion years of planetary evolution. We arrived. It's Christmas. Okay. Look at this great treasure there is. There are all the minerals here. There's the oil. There's the coal. There are the trees. There are the soils. All there for our use. And all of them developed over thousands to millions to billions of years of Earth history. And we're able to use them all suddenly. So here is the buildup of oil over Earth history. It started building up a couple 100 million years ago. It gradually builds up until the present day. And then there's a vertical cliff here because we're going from there to there. Earth is still making oil. Not to worry. It makes oil at the equivalent of one Boston gas station. So, one Boston gas station pumping over 400 million years makes Earth's oil resources, oil and coal. So we live in the fossil fuel age. Here it is from the long-term perspective. Here I've changed the scale, so that's 10,000 years ago, not using any oil. We start to use oil at the end of the 19th century, and we'll use it all up, and then it's gone. So we live in the age of fossil fuels, a unique and amazing moment in planetary history, where one species is able to take advantage and use, in a few hundred years, the entire treasure built up over hundreds of millions of years of Earth history. That's the human energy revolution. It's a transformation of planetary functioning. And if you look at it from this perspective, you can say, well, there's a kind of a time frame here. Ultimately, we're going to want to pass from the fossil fuel age to being able to use wind and solar and ultimately fusion. Yes, fusion, we say, oh, gee, when's that going to happen? We're still thinking in decades, hundreds of years. If you think of over thousands of years, ultimately that occurs. So we have this sort of jump start to technology and energy use provided by the planet, and we have to successfully traverse that jump start so that we can access other sources of energy after those fossil fuels are gone. There's also been a human relationship revolution. Perhaps the most obvious and striking is language. We are able to communicate with each other and around the globe, and therefore enter into retained knowledge and exchange that is not possible for any other species. We have the opportunity of global sensing now with satellites and networks. We have global communication. If any of you have Skype on or WhatsApp or some application, you may be communicating right now with people in Asia or Europe. We have the ability to relate to scales larger and smaller than ourselves, and particularly we have the ability to ponder and relate to the cosmos as a whole, something where there's never been that capacity of relationship before. We also have the ability to undertake directed evolution of other species, and we are at the frontier, but it will happen, of new capabilities from the coupling of biology and technology. As one of my colleagues said once, I want a chip that puts Google in my brain. It will happen. And so we propose that human civilization is in fact a new eon in Earth history. We divide geological time into different units. There's epochs, there's eras, periods, eras, eons. And Paul Crutzen at MIT proposed that the arrival of human beings on the scene created a new epoch, which he has called the Anthropocene. But when we were pondering all these changes that have occurred as a consequence of human beings, with the energy revolution, the relationship revolution, the massive environmental change, the fundamental modification of biological evolution, the ability to specialize within a species where no one of us knows much, but all of us together know an awful lot. This is a revolution in the relationship within the species and to the planet that, if we survive, will mark an entire new stage of planetary evolution that we cannot really even imagine. And of course, accompanying this are all the environmental problems. We, of course, all hear about global warming every day, but one of the things we wanted to emphasize in the book is that it's not just global warming, that water resources and biodiversity are equally troubling, and we live on the edge. People wonder about evolution. Evolution has two modes. It has species creation, which is a little tiny step-by-step change of species until they just diverge enough to be different. And species extinction, which is the fundamental change of the end of a species, which we're also aware of. Why are we aware of it? Because the rates of extinction of species over the last 50 years or so is about 10 million times the background level over Earth history. So we can argue about whether we are the products, we are creating a mass extinction or not, but whether it's a mass extinction or not, this extinction half of evolution is something that we are having a profound impact upon. Satellite data now show us the depletion in Indian groundwater. This is one of the most densely populated regions on the planet, and the groundwater is dropping at a few centimeters per year. It's not a problem right now. that continues for long periods of time, it could lead to massive famine. I don't know whether you all realized it, but North America used to have a greater diversity of large mammals than Africa. And the destruction of those mammals occurred with the arrival of human beings in North America. This has been something highlighted by E.O. Wilson, where he's made this beautiful diagram showing what happened after human beings arrived on a continent, especially if they arrived suddenly. There have been human beings in Africa for a long time, so it's been gradual. They arrived suddenly in Australia, boom. Suddenly in North America, boom. Suddenly in New Zealand around 1600, boom. That is the effect of human beings as we look for food and take over habitat. And Wilson has also pointed out that the number of species that you get depends on the size of the reservoir in which they can actually work in. So it's not just a matter of preserving a species here or there. The total number of species depends on them having a critical size in order to be able to survive. We are cutting down the rainforests. It's gotten a bit better in the last year, particularly in the Amazon, but not in Indonesia and not in the countries that surround Brazil. It's gotten better in Brazil. This is the number of square kilometers from 1978 through 2004. You can see the slight increasing trend. Bar graph doesn't convey very much. You'll all recognize this map. Yankees. Boston Red Sox, Martha's Vineyard. And that box is the amount of rainforest that is cut down annually. We just don't realize the extent of what's going on. Much of it for the creation of palm oil, which we use in most of our foods. So we are in fact quite responsible for it. Now, this overall modification, destruction, change of the environment is closely related to the environmental problem that is not on the table. And that problem is human population. So this is a log scale, and this is human population going back to about 10,000 BC. There was a time, 10 or 20,000 years ago, when it's thought there may have been only a few 100,000 human beings on the planet, maybe as few as 10,000. And then that gradually grew, and even at the time of, this growth rate is extremely slow. At the time of the developments of civilization in the Roman Empire, there was stability and population growth. We entered the Dark Ages, population flattened out, and then we had the Industrial Revolution, and that led to this change. Now, when you look at a diagram like this, when it's on a log scale, exponential growth is a line. So that would be exponential growth. We are super exponential growth. And you can do that by plotting the growth rates versus time. So human population had a growth rate of less than 0.2%, 0.1% from 1500 BC to 1500 AD, and it's gone up to greater than 1%. You can also think of this as doubling time. Doubling time is 72 divided by the growth rate. So when we're down at 0.1, the doubling time of human population is 720 years. When we're up at 0.6, the doubling time of human population is about 40 years. So we're at 7 billion, we're going up to 12 billion. Now, that means you can imagine the change in impact from having the population you'd have in 1600 versus the population today, even in the absence of any change in technology. If there were a huge catastrophe such that 97% of the people on Earth today were suddenly exterminated, Earth would have the same population it had in 1650. We look back in history, there was a lot going on there, many great discoveries. We're 30 times more abundant in population. That's one of the reasons for the rapidity of change, both in human civilization and in the Earth. Now, our whole model is based on economic growth. And so this is a plot of the total primary energy use per person versus the GDP. And here we are out here in the United States. We have the most energy use per person, and we have the biggest GDP, and there's a remarkably good correlation. If you want a big GDP, you've got to use more energy. And we have the less energy efficient countries like Canada, the Soviet Union, the Middle East. Those will all ring bells with you as countries that have a lot of fuel resources. And we have places like Europe and Japan. Western Europe, Japan have approximately the same living standard that we do, using half as much energy as we do. This energy use depends on CO2 currently. So the amount of CO2 emitted per capita correlates very closely with the total primary energy. You also have slight differences here in efficiency. So you have the USA and Australia, very inefficient, and you have places like New Zealand, which is much more efficient. So I was thinking of maybe entering the presidential race. I know it's a bit late, but I have a great platform. First, stringent restriction on population. Second, no more economic growth. Vote for me. So we face a problem, right? Because the entire model on which our political system is built is based on economic growth, and the entire model of economic growth is based on energy, and the entire amount of energy depends on destruction of the environment and production of CO2. And population is at 7 billion and maybe going up to 12 billion. It's politically taboo to talk about the really fundamental environmental problem, which is population growth. If we could peak it at 7 billion instead of 12 billion, our total environmental impact is population times energy, and suddenly we've reduced the impact 50 years ago by a half, simply by capping the number of people on Earth rather than having it continue to grow exponentially. Final thing I want to convey, I'm sorry I've been talking too long, but the final thing I want to convey is the time scale on which these events are happening, and that we are living in an amazingly exciting moment of planetary evolution. And I'll try to convey that by relative time. So you kind of think of the Earth as an animal. What do things feel like for the Earth? It has a total lifetime of 10 billion years. It's not old yet, it's only 45 years old because it's 4.5 billion out of 10 billion. And we use this often when we talk about dogs. Those of you who have kids, you know that man years to dog years is about 7 to 1. So possibly your dog is whining at the door, and your child doesn't want to take the dog out. And you say, you know, when you make the dog wait for 20 minutes, that's like making you wait for 2 hours. Because the dog feels time 7 times more intensely than you do. So we can turn that around, and we can look at a relationship of Earth to man, and that turns out to be 100 million to 1. So 1 relative year for the Earth is 100 million human years. So from the perspective of planetary evolution, we can look at the relative durations of things. Human beings, if we're lucky, live to be 100, youth, maturity, and death. The Earth lives to be 10 billion, youth, maturity, and death. And we just have to scale that time frame. So what does time feel like for the Earth? And so it turns out, if you kind of divide things up, 1 pulse is about like 1 cycle around the sun. And the duration of an Earth day is about like an ice age cycle. And the duration of an Earth year is something like a geological period. And we can consider the appearance of human beings on that time frame. We're changing Earth in the blink of a planetary eye. The final thing that we try to deal with in the book is this question of life elsewhere in the universe. And, you know, we've only been sending radio signals out for a few years. And so they're only able to travel a few light years. The Milky Way is 100,000 light years across. And so our expression can't go anywhere. So when you ask, why aren't people coming and seeing us, or maybe they are with the crop circles, but why aren't they really? And you say, well, come on, we just appeared. The other thing is that if you consider the likelihood of civilizations on other planets in our galaxy, you can write this as a whole series of probabilities. And it turns out that the most critical term is the lifetime of a planetary civilization that has technology. So, if you take the Earth, we've had technology for 100 years out of 4.5 billion. So if you were to visit Earth or take a quick look at it, you would have the chance of 100 divided by 4.5 billion of finding intelligent life on it. Okay, so the average duration of a species is about 10 million years. Maybe intelligent life is, once it takes over a planet, is able to persist for hundreds of millions of years. In that case, there's intelligent life all over the galaxy. Thousands and thousands, millions of intelligent civilizations. Only if they've persisted for hundreds of thousands to millions of years. Where have we come in the last 100 years? Now, imagine a civilization that has had technology not for 100 years, not for 200, not for 1,000, not for 10,000, for 1,000,000 years. We can't imagine. We are more primitive than a universal caveman. There may be means of communication among these kinds of civilizations that we have no idea about, just as we have so little idea of 96% of the universe in dark energy and dark matter. Just as whenever we ponder the mysteries of quantum mechanics, we see that there's all these things about the universe that are very difficult to understand in our ordinary human mind. And so if there's life else out where in the universe, it's done two things. First, it's been able to overcome this challenge of planetary destruction versus planetary nurturing. And it is incredibly advanced in ways that we cannot even imagine relative to our own. So I'd like to just close with this thought, that we are privileged to live at a moment when there's the grand challenge of human civilization, when there is a grand possible threshold to planetary evolution that we can either meet or fail at. And one of the steps, surely, is to pass from being a planetary user to basically being like a 2-year-old, thinking that everything is there for us to play with and it doesn't matter if we break it, to a planetary conservator, that is, to being more adult. To realize that we are part of a natural system, inevitably linked to it, that we are possibly a part of the evolution of that system, and it would be our privilege, our role, our goal, to participate in that evolution rather than to pursue our egotistical personal goals. So only to the extent that life elsewhere in the galaxy has met this challenge is life abundant in the universe. And only if we are able to meet this challenge will we ourselves be entitled to become members of this galactic community. Thank you very much.